Hey everyone, this is 12.1 Intro to Counting. It's kind of a funny name, I know, because you probably think you already know how to count. But here we're going to be interested in how many ways can we perform a certain task. So for example, let's say you have a bookshelf with 5 slots for books and you have 5 books. How many different ways can you arrange those books in a certain order? Or let's say you have, a common question is like you've got 3 suit jackets and 5 shirts and 2 ties. How many different outfits can you make out of those combinations, right? So that's the kind of thing, type of problem we're going to be tackling in this section, or actually in this chapter. So let's get to it. All right, on page 612, we're going to work on number 1 here. We have this set of people. U stands for Carrie Underwood, C for Kelly Clarkson, D for Chris Daughtry, etc. These are all just representing people from American Idol. And what we're supposed to do is list all the ways you can make the selection described. So for number 1, it says select 2 singers. So we're taking 2 of these 5 objects without repetition, so no repetition, and order is not important. That's what this UC equals CU means. This means as long as you select a U and the C, it doesn't matter if you flip their order around, right? That's what they mean by order is not important. So we're not going to list these 2 outcomes here as separate outcomes. It's actually the same thing, so we'll just list UC and we won't even worry about CU. Okay. So we're just taking 2 out of this set, and this is set notation up here, by the way. They just call it the set W for some reason, and these little braces just mean we have a set, and we have these 5 objects in the set. They're letters, they represent people from American Idol. Okay, so let's start listing. The easiest way to do it is to start with your very first object in the set, U, and then see how many pieces you can pair it with. So obviously U and C is one choice. And then you could pick U and D, or U and B, or U and A. That is all of the outcomes with U. Notice we couldn't use UU because no repetition is allowed. So these are the only outcomes we have with U. Now if you go to the next one and start with C, notice we're not going to go backwards and count CU because we already said UC and CU are the same thing. So we're just going to go forwards, and also obviously we're not going to choose CC. So we're going to go forwards and choose CD, that's one of the outcomes, CB, or CA. Right? And paired with that UC that we already have, that's the 4 outcomes we can get with C. So we'll keep doing it. We'll go with D and go forward. DB we can do, and DA. And then our last choice now is just BA. So these are all the different outcomes we can have. If there are no repetition, we're choosing to, and order doesn't matter. Alright, so same idea here on number 4, except this time, same set, they still want us to choose 2. This time they tell us that we have repetition. Select 2 singers with repetition, and order is important. So UU is allowed, for example, and DB is not the same as BD. So we're going to start the same way. We'll start with U, but this time the first thing we can put U with is U again, because repetition is allowed. And then we can do our UC, UD, UB, and UA. Right, and then we'll start with C. Now we can go backwards this time, so I would just start with CU, then I would go to CC, right, because we can put C with itself, we can put C with U, and then go forward CD, CB, and CA. And so on. With D we can go DU, DC, DD, DB, and DA. And then with B, the same thing, kind of gets tedious after a while. BB, BA, and then lastly with A with every single value up there. A and U, A and C, A and D, A and B, A and A. There we go. So this is what you get if there's same job essentially, right? We're selecting 2 from the list. This time repetition is allowed and order is important. So these are kind of weird problems, but we're essentially just making lists. We're trying to be systematic about it, and we're trying to be careful about these rules. The whole repetition and order mattering, that's going to be pretty important later down the line when we do more complicated problems. If you're looking for why are we doing this maybe, just imagine at American Idol they're going to have they're going to choose 2 of the old contestants to I don't know, come up and perform. The first option was no repetition and UC equals CU. So in that situation, obviously they want to choose two of them, right? So maybe they have like a duet or something like that. So you have to choose two people to sing it, and it doesn't matter what order because they're going to be singing together, right? It's like a duet. So that's kind of one way to give you an example of the number one, where there's no repetition and the order doesn't matter. Here in part 4, though, we do have repetition, and the order doesn't matter. Sorry, the order does matter. So maybe they're just choosing, they have two songs that they want sung, and the same person can sing the song, right? So both songs. So like you might be Carrie Underwood sings the first song, and she sings the second one. Notice UC and CU here. UC would mean Carrie, I don't know if I have these names right. Carrie Underwood sings the first song, and who's C? Kelly Clarkson sings the second one. Notice that's different from CU, because if these slots here are representing like the first song they choose and the second song they choose, this would be backwards. This time she's singing the first song, she's singing the second song. So you can put these into context. Obviously our goal here is to just kind of abstract this right now and think about making lists, choosing with repetition or without it. Alright, on same page, page 612, if you look at numbers 5 through 8, it says draw a tree diagram that illustrates the different ways to flip a penny, a nickel, a dime, and a quarter, and use this diagram to solve some problems. Tree diagrams are notoriously not maybe a little bit difficult, a little bit confusing. As you can see, there's a lot of stuff going on here. I've mostly did the tree for you, but let me kind of break this down for you on how we could do this. So I started with P, N, D, and Q. These are representing our flipping a penny, nickel, dime, and quarter. And over here I'm starting with our very first choice, P. What happens when you flip a penny? Well, there's two options. You could either get a heads or a tails, right? Regardless of what option you have, your next task essentially is to flip the nickel, right? And then when you flip that nickel, obviously there's two options. There's heads and tails and heads and tails. And so this tree, if you follow down, one of these paths, you will get an outcome. Like, let's say I go this way, this way, this way, and this way. This is the outcome where the penny was heads, the nickel was tails, the dime was heads, and the quarter was heads, right? Heads, tails, heads, heads. Right, so each of these little branches here are going to represent different outcomes. Let me show you just filling in some of these other branches. So like if you go down, let's try to find this branch here, right there. So you flip the penny, you get tails. You flip the nickel, you get heads. You flip the dime, you get tails. And you flip the quarter to get tails. So our outcome there will be tails. Gotta write kind of small. It'll be tails. Then it was heads. Then it was tails and tails. Right? That's what that branch represents. It represents the penny was tails, nickel was heads, dime was tails, quarter was tails. So let me just fill in a couple more of these branches. This next one would be tails, tails, heads, heads, it looks like. Tails, tails, heads, tails. And at the bottom, it's almost all tails. So it's tails, 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 heads for the first one. Tails, tails, heads. And the very last one is all tails. Notice this is the only outcome where all the flips are tails at the very bottom. Similarly at the top, this is the outcome where all of the flips are heads. Okay, so this is what a tree diagram looks like. It can get very messy very quickly. Notice we only had 4 little tasks here, and each task only had 2 different outcomes. And even still, we get a bunch of outcomes here. In fact, if you count them all up, there should be 16. I'll give you kind of a preview of things to come here. If you think of this as 1, 2, 3, 4, we're flipping 4 coins. Each coin has 2 options, right? And if you multiply 2 times 2 times 2 times 2, you will get 16. That's the quick way to find out how many options there are. But notice the tree actually gives us not only how many options, it gives us the individual unique options. So we can actually follow the branches and figure them out. So we're going to need that ability to solve these problems. So number 5 says, in how many ways can you get exactly 1 head? So we need to go through all these branches and pick out all of the outcomes that have only 1 head. Well, let's see. Where's the first one? Right here. Oops. Right there. Right, heads and all tails. what's the next one with just one head? There's one. And the next one, there's one, and there's one. Right, so I'm literally just going through and finding all the ones that only have one H. It looks like there are 1, 2, 3, 4. There are 4 ways, 4 different outcomes that have only one head. So let me go through and erase these real quick. Alright, let's do the same thing for number 6. This time it says, in how many ways can you get no tails? Well, notice no tails is the same thing as all heads. There's only one here, right? This is the only one with all heads. Every single other one will have at least one tails. So there's only one outcome where there is all heads, which is no tails. And how many ways can you get exactly 2 tails for number 7 here? So 2 tails. Erase this real quick. So 2 tails. So let's go through 2 tails. So notice 2 tails means 2 heads and 2 tails, but either way it's going to be 2 tails. So that's one, that's one, that's one, that one, that one, that one, and I think that's it. 1, 2, 3, 4, 5, 6. 6 different ways you can have exactly 2 tails. And lastly, number 8 here, it says, how many ways can you get exactly 3 heads? Same thing, let's go through and pick them out. Here's 3 heads. 3 heads is the same thing as 1 tail, by the way, so 3 heads, 3 heads, 3 heads, and I think that's it. I got 3 ways. Oh, I think I'm missing one, hold on. 3 heads, 3 heads, ah, there it is, missed it. 3 heads, so there's 4 ways. Okay. So notice these questions are pretty easy to answer if you have the tree diagram. So the tree diagram is kind of the work for this type of problem. Don't beat yourself up too much about tree diagrams. I'll be honest, I don't think there are any problems on the homework or test that you have to solve using a tree. There's almost always other ways you can think about it or other ways you can come up with it. Even with this problem, we probably could have just listed these combinations out without actually giving the tree. It's just that the tree is the most kind of formal, systematic way of coming up with all the options and making sure that you don't leave any out. Like I could probably just tell you, come up with a list, a string of H's and T's, representing all the different ways you could flip 4 coins. You could probably list a bunch of these, but you probably would either miss one or list one twice. The tree is a nice systematic way of breaking that down. Alright, so page 612, number 9. This one says, how many different 2-digit numbers can you form using the digits 1, 2, 5, 7, 8, and 9 without repetition? For example, 55 is not allowed. So this is very similar to our first problem, right? We're just picking 2 numbers out of the list, and repetition isn't allowed. Notice order matters, right? So like 1 and 2 would be 12, but 2 and 1 would be 21. So those are 2 different outcomes here. I want to point out to you that doing this with the tree is bad news. This is kind of what the tree would look like. This is like your first pick. So your first pick, you can choose from any of these, 1, 2, 5, 7, and 9. Let's just say your first pick, you picked 9. The next thing you have to do is pick your second number. So because repetition is not allowed, notice I only have 5 branches versus the 6. So I start out with 6 numbers I could choose from, so 6 branches. If I choose my first number as 9, let's say, I only have 5 branches left because I can't choose 9 again. So then I can choose 9 and 1, 2, 5, 7, or 8. Well, let's say I choose 8. So I picked a 9, picked an 8. Oh, these are only 2 digits. I guess I should have made the third tree, but either way, this last part doesn't count. I guess I was assuming we're going to keep picking. So just focus on this first 2 lines here. This is just one choice. If you go to the 9, and then you can pick any of these, right? Well, off of the 8, there also has to be 5 branches, and then you would have the 1, 2, 5, 7, and 9, right? Because you can't pick the 8 again. Off of the 7, you would have 5 branches. You'd have the 1, 2, 5, 8, and 9, everything but the 7. This tree is going to look really, really messy. It's going to be hard to draw, and it's not really going to be worth it, right? Because we don't need the outcomes. We just need to know how many, right? So if you just need to know how many, the easiest way to do it is with what we call the slot method. So let's make 2 slots. The first slot is going to represent the number of choices we have for the first number. Well, we can choose any of the 6 numbers for the first number, right? 1, 2, 5, 7, 8, or 9. So that means this first slot we're going to have 6. We can choose any of the 6 numbers. Now for the second slot, since there's no repetition allowed, whatever we pick for the first slot, we can't pick that again for the second slot. So that only leaves us with 5 other numbers we can choose from. Right, so notice 6 and 5, 6 isn't on this list up here, right? Because 6 doesn't mean we're going to pick the number 6. 6 here means there are 6 numbers to pick. 5 means there are 5 numbers left to pick after you pick your first one. And if you want to figure out all the combinations together, you multiply them. 6 times 5 will give you 30. And that's how many different 2-digit numbers you can make if you have no repetition, right? And this is the same thing you'll get if you actually go through and draw all these branches, which will be a pain, and you count up how many options there are at the end. You'll still have 30 total branches at the end. But it's just a lot more work, and it gives you more information that you need. All these branches will actually list all 30 numbers, but we don't need that for this problem. We just need to know how many. So the easiest way to do it is just 2 slots, because we're picking 2 numbers. How many options for the first slot? How many options for the second slot? Multiply them together. Alright, same idea in here in number 12. We're going to skip the tree and just go straight to slots. It says, how many different 3-digit numbers can you form using the digits 1, 2, 5, 7, 8, and 9 with repetition? So let's just start with 3 slots. We're picking a 3-digit number, 1, 2, 3. There are 1, 2, 3. There are still 6 numbers to choose from, so this is with repetition. So for the very first slot, we can choose any of the 6 numbers. Now, because it's with repetition, it doesn't matter what we pick for the first slot. The second slot, you can still pick any of the 6 numbers because we can repeat this time. So we're still going to have 6 options for the second slot. And again, with repetition, we got 1 more slot. We can pick any of the 6 options for the third slot. So 6 options for each slot. If we want to know how many ways we can do it all together, sorry, I'm trying to show my multiplication dots there. It's going to be 6 times 6 times 6, which gives you 216. So it turns out you can make 216 different 3-digit numbers out of these 6 numbers, right, with repetition. So that just means we can choose numbers like 111 or 222, 555, right? But there are 216 different numbers altogether. Using repetition, shuffling all the numbers around, 216 different numbers we can make. Again, notice it doesn't give you the 216 numbers, but can you imagine having a tree with 216 branches at the end? It would be very difficult and very time-consuming to draw. It would be very tedious. So if they ask you just how many, the easiest way to do it is with slots like we just did. Okay, similar problem here on page 612. This one in the italics, it says, assume you're rolling 2 dice. First one's red, second one's green. That doesn't really matter. They just want you to make sure that you know that you have a first dice and a second dice, right? Or a first die and a second die, 2 separate dice. Use a systematic listing to determine the number of ways you can roll each of the following. For example, a total of 3 can be rolled in 2 ways, 1, 2, and 2, 1. So the questions, for example, like on 13, it's going to ask you, how many different ways can you roll a total of 5? So you're rolling 2 dice and you're adding up the numbers that you get. So that's why this example here, they said if you want to roll a total of 3, there's 2 ways you can do it. You could roll a 1 first and then a 2, or a 2 first and then a 1. So the first thing I did is I went through and I made the whole table representing all the different outcomes when you roll 2 dice. This is just like a common type of problem when you roll 2 dice. There's a lot of different questions we can answer. Even later in chapter 13, when we talk about probability, there will be similar questions, and this kind of table here will still be useful. So I actually recommend you write this table down, you put it on a note card, and you use it for the final exam, for example. Not saying that the problem is going to be in there, I can't actually remember, but it is, at the very least, on like the chapter test for this chapter, this will be a useful thing to have. So let me just go through and explain to you what this means. This first column, 1, 1, means first dice is a 1, second dice is a 1. 1, 2 means first dice is a 1, second dice is a 2. Right, so I just went through and I listed all the ways you can roll a 1 first and then any other number second. Then all the ways you can roll a 2 first and any number second, a 3 first, 4 first, etc. And then all together, this is a 6 by 6 kind of table here, right? You're going to get 36 total options altogether. Really quickly, notice if the question was simply how many options are there when you roll 2 dice or how many different outcomes, you could do it with the slot method. Right? When you roll your first dice, there's 6 outcomes. When you roll your second dice, there are 6 outcomes. 6 times 6 gives you 36. Right, so the slots here would give you the number of outcomes. This table, this listing, gives you the actual outcomes, right? And I guess you could do this with a tree too, but again, it would be cumbersome and complicated, and you would get the same results, it's the same number. Okay, so let's tackle these actual questions. 13 says, how many ways can you roll a total of 5? So the cool thing about having this table here is you can see on the diagonals where it is. Like if you go down your first column, you can roll a 5 if you roll a 1 and a 4. If you go in the second column, you can roll a 2 and a 3. Third column, a 3 and a 2. Fourth column, 4 and a 1. See this diagonal I'm talking about? 4, 1, 3, 2, 2, 3, 1, 4. That's where all the 5s occur. So the answer to this question is 4, right? Because there's 4 ways you can do it. I'm going to go ahead and list all the different outcomes, though, just so you actually know where we're getting this from. So the 1, 4, that's one of the outcomes. The 2, 3, the 3, 2, and the 4, 1. Right, so those are all the different outcomes we have, and I just want to quickly put the answer in over here. So the answer is 1, 2, 3, 4. There are 4 different ways we can roll a total of 5, and I've also listed the ways we can do that. Alright, so again, once you have this table, answering this question is pretty easy, I think. Let's do the same thing for for number 14. It says, how many ways can you roll a total of 7? Well, we could do a 1 and a 6, right? 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1. Notice this is the longest diagonal, so this is also the rolling a 7 is also the there's the highest number of ways you can do it. That's what I'm trying to say. So let's list them. 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. There are 1, 2, 3, 4, 5, 6 ways, so the answer to this problem is 6, because they want to know how many ways. I'm just go ahead and I'm actually listing them out so you can see all the ways. Right, so 6 is the answer to 14. And lastly here on number 15 it says, how many ways can you roll both numbers the same? Well, we can also figure that out pretty easily, right? Because that's our other diagonal. It's the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. I'll list them for you, but it's pretty obvious. It's also, the answer is going to be 6 again. 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. 1, 2, 3, 4, 5, 6 different ways you can roll both numbers the same. Right, so we're just simply using this table to answer some of these questions about how many different ways you can do things. The other questions, if you look at like 16, 17, and 18, you can try these out pretty easily. How many ways can you roll a 3 on the red die? Which one was red again? The first one is red. So that's pretty easy from the table. Here's all the ways you can roll 3 on the red die. It just means the first number is 3. Looks like 6 ways as well, right? So it doesn't really matter what the question is. If you have the table, you should be able to figure it out pretty easily. Okay, last problem here, page 612. It says, recall an example 6. So go back and check out example 6 if you're interested. Maya has designed different tops, pants, and jackets to create outfits for Project Runway. How many different outfits can her models wear if she has designed the following? So she's designed 6 tops, 5 pants, and 4 jackets. Again, we are just counting these up. We're not trying to list them out. Not that we could, because we don't know anything about these tops, pants, or jackets. So let's just make slots for each. Tops, pants, jackets. I'll go ahead and label them. Tops, pants, and jackets. And how many different combinations can she make out of these pants, tops, and jackets? Well, she has 6 tops to choose from, 5 pants to choose from, and 4 jackets to choose from. Notice picking one of the tops doesn't affect your next choice, like what pant you pick or anything like that. So each of these is just 6, 5, and 4 in this case. We don't have to worry about things like repetition or order mattering, because each of these things are just different and we don't know anything else about them. So that's it. 6 times 5 times 4. Multiply this all together if we want to get the total number of ways, and this will give you 120. Again, you could try to list these out. You could try to make a tree diagram, but it's going to be time consuming, it's going to be difficult, and it's going to give you more information than you need. If you just want to know the number of ways you can do something, slots are the quickest way to do that. So just kind of a little summary here about the different methods we have. Lists, trees, and slots. Lists and trees will give you the number, so that it'll give you the number of outcomes and the actual outcomes that you can get, but they can be difficult. Lists, for one, lists are great if you can list them, but especially when things get more complicated, like if you think about flipping those coins, it's hard to know if you've listed all of the outcomes. If you haven't, it's hard to know if you haven't forgot one. It's hard to see if you maybe have listed one twice. So those are kind of common things that happen. Trees are a little bit better than lists in general because trees are a systematic way of listing, essentially. If you draw the tree out, and if you do it correctly, then you shouldn't have any doubt whether you've missed an outcome or if you've counted an outcome twice. But trees are difficult to come up with, they're difficult to draw, they're tedious, there's a lot of stuff going on. So you only use those things if you have to actually know the number of outcomes. And realistically, if your set gets large, like think about we were flipping 4 coins. Well, what if we were flipping 10 coins? Drawing a tree for that would be outrageous. It would take a long, long time and would be very difficult. So as the number gets higher, lists and trees just simply get impractical. Like they're not worth the time. So slots are what we're going to use if we only want the number of outcomes, and it's actually what we're going to use the most. But it is fast, right? So obviously the downside is it doesn't give you the actual outcomes, but it really quickly can give you the number of outcomes. And we've been kind of cheating a little bit when we use slots, actually, because that's what the next section is about. Because every time we use the slots, we're using what's called the fundamental counting principle. And all that counting principle means is, like if you have these slots and you have X ways to do one thing, Y ways to do a next task, and Z ways to do your third task, the question is, well, how many ways can we do the whatever this overall task is altogether? Well, the fundamental counting principle is what tells us that if you multiply them all together, that's how you get the total number of outcomes. So X times Y times Z in this case. So that uses what's called the fundamental counting principle. It's pretty basic, but that's kind of what 12.2 is about. So that's what we'll tackle there. Probably some more complicated problems too. We'll use lots of slots. We won't really be worried about trees. So just so you know, a lot of students get stressed about the tree thing when they see it. A lot of the problems on my math labs also say, oh, well, do this problem by visualizing a tree diagram. Well, it's kind of difficult, to be honest, because the tree diagram can be pretty complicated. So I recommend that, and like I said, I don't think there are any problems that require you to draw a tree. It's just that drawing a tree is kind of a good exercise, helps you visualize things, and it will give you some good information. But I think you can get away with either lists or slots for all of the problems. So there you go. That's it for 12.1. Let me know if you have any questions, and keep up your good work.